Hi everybody and welcome to the Optimization Masterclass. This is Giordano Scarciotti. I'm an academic at Imperial College London. Some time ago I released a video on how optimization is used in aerospace applications, and many of you asked me to release additional material on optimization. I promised you that I was going to do that, and finally I found the time to put together some of the material that I had lying around. So my objective with the Optimization Masterclass is to teach optimization, not much more than that. I have an open-ended plan for this masterclass. It means that I know where I'm starting, but I don't know when I'm going to stop. I will start with this book, so to cover this book, Convex Optimization of Stephen Boyd and Jeven Vandenberger. It is an excellent book, but actually the reason why I'm covering the book is not because of the book in itself, but because the group behind the book created a toolbox called the CVX. So it's a programming toolbox, which is very good, very easy to use, and that's why I'm using their material, okay? Because I really like CVX. So as I said, I will start by covering this book, and after this is finished, I may cover additional topics, depending on how the series is going, if it's appreciated or not. I also want to clarify that even though I'm going to release these lectures, I will continue to make videos about all other stuff on the YouTube channel. So this YouTube channel will not just become a YouTube channel about lectures. There will be lectures, but there will be also other content that talks about engineering and science more in general. So this is a very popular book, and there are already other lectures available on this book, and in particular there is also a wonderful video lecture of Stephen Boyd that follow very closely the book. And so I ask myself, what is the added value that I'm providing with these video lectures, with this masterclass? Well, first of all, I start from convex optimization, but then I will go to cover other topics. But secondly, I'm actually releasing to you what I call smart handouts. So what is a smart handout? So a smart handout is essentially a Python notebook, which I share with you through Google Colab. So this means that you can import this file on your own drive, and then you can actually edit this file, you can run it, you can change the code, and so on. Okay? So why I call this smart handout? Because the smart handout essentially blends videos. Now, it's not present in this screenshot because I'm actually creating the video now, but there will be a video on this file, which is this recording that I'm doing right now. There are going to be figures, there are going to be codes that you can run, so you can actually run this code, you can change it, and so on. So it's essentially a blend between recordings, text, exercises that you can solve, examples that you can run, code that you can edit as you want. It's a very good resource for you to have and to play around. And also, if, for instance, there is some piece of knowledge that you don't know, so for instance you don't know the meaning of a specific mathematical concept, you could just add or modify the handout to explain yourself that concept. In terms of background, I assume that you have the background of a second-year engineering student. That means that theoretically, I expect that you know what is a gradient, what is a nation, and you have some linear algebra background, so that you know what is the rank of a matrix, what is the image or range, you may call it either way, or the kernel of null space, again you can call it either way, of a matrix. From a practical point of view, you need to know at least one programming language. We're using Python in this course. We will use Python, but our Python is going to be simple. So as long as you know well a programming language, I'm pretty sure that you will be able to follow the rest of the course. Okay, so not much more than that. It's needed to follow the course, but of course you need to have that background, or you need to be in a position to be able to grasp that background by yourself. The way to find the smart handout is just to go in the links down below the video. So you open the description and then you will find the link to the Google Colab, and then from there you can import the notebook in your own drive. So let's see in practice how a lecture will work in this series. So as I said, the aim of this Optimization Masterclass is essentially to explore the wonderful world of optimization. We know where to start. We will start with the book of Stephen Boyd and Jeven Vandenberger on Convex optimization, but later on we will explore other topics. The way of delivery of the series, it's video lectures. Some of them are based on a course that I run at Imperial College London, and then I will release this, you will have access to these smart handouts where you can essentially play around with the exercises code and so on. Okay? So I suppose that you know why optimization is useful, otherwise you wouldn't be still here, but just to be clear. So optimization provides a rigorous mathematical framework for systematically determining the best possible outcome from a set of available alternatives under constraints. Okay? So that means that practically anything that we do is actually an optimization problem. We always want to get the maximum reward from something that we do in the least amount of effort, right? Can simply be something like, for instance, doing the best route to get to a place. We want to do this by minimizing the amount of time that it takes to go to the place, right? So we're always solving optimization problems in real life. So optimization as a field is a branch of mathematics in which we want to find a systematic way to find solutions to complex optimization problems. And any industry is actually using optimization in some form because, again, they want to maximize their profit and they want to reduce their cost. So let's look at three classical examples. So the first example is the traveling salesperson problem. Okay, so what is the problem? Well, you can think of it as the Amazon problem. So the problem of starting from a certain depot, and then the driver needs to visit various locations to leave the packages. And of course, the driver wants to do this in the most efficient way, because this will reduce, for instance, the time working, and will reduce also the cost in terms of fuel. And for instance, here there is a simple instance of the problem in which we start from the depot and then we go and visit some of the location in this order. And this is actually not an optimal solution. While if we go on this other graph on the right hand side, we see that an optimal solution that actually minimizes the distance, the total distance traveled is the following. Now, this is a very simple instance of this problem, and you can solve it by just looking at it. But the problem, of course, should be applied to thousands of locations, and then it becomes complicated. Now, this is a hard problem for which there are very good approximate solutions or even exact solutions for problems up to a certain relatively large size. But the problem in general is difficult to solve. So if I give you 1 million of locations, then this becomes a difficult problem to solve. The second example that I want to mention is the resource allocation problem, which is again, a very classical problem which basically every company tries to solve, maybe even without realizing it. And in this specific example, what we have is our objective is to maximize the profit. Now, our company produces chairs and tables. Okay, so we build chairs and tables. And the way we get our profit, it's a combination of selling a certain amount of chairs and a certain amount of tables. So we can think of our objective function as the cost of a chair times the number of chairs plus the cost of a table times the number of tables that we produce. Okay? So we want to maximize this profit, but at the same time, we are under certain constraints. What are the constraints? Well, to build chairs and tables, we need certain resources. And the resources are wood and labor. And to build chairs and tables, we have different combinations of these resources. For instance, to build a chair requires less wood of building a table, but it requires more labor because it's a more complicated object. So we may have constraints on how much wood and how much labor we have available, right? Because, of course, that's a limited resource. And the way in which we consume these resources will depend on how much labor and how much wood it's required to build each one of these items. For instance, we can imagine that the wood constraint is going to work in the following way. So as the number of chairs that we build plus 2 times the number of tables has to be less or equal than 10, okay? So an arbitrary value. And for the labor, we may have a similar type of constraint in which we say, okay, to build a chair, it takes more effort. So 3 times the number of chairs plus the number of tables has to be less or equal than 12, okay? Now, this is a very simple problem. It's a linear program. It's called a linear program. We will see later why. For us, it doesn't really matter because we will treat this as a convex optimization problem anyway. So whether this is linear or quadratic doesn't really matter. And it's also such a simple problem that we can solve it by just making a sketch. And this is what we are looking at here. So the idea here is that we have our wood constraint, which is essentially this blue line over here. And we know that the constraint is that the amount that we can consider has to be below 10. So that's to be below this line over here, okay? Now, if we look now at the labor constraint, which gives this line over here, we know that we need to be below this line, so we need to be in this region over here. Once we take the intersection of these two regions, we get this gray area over here. Now, this is also considering the constraint that the number of chairs and tables are positive or at least non-negative numbers, okay? So that's why we're looking just at this part of the Cartesian plot. So that means that we can look at a solution only in this region here, because this is the region that satisfies both our constraints. And this is called the feasible set. Now, how do we find the solution in this graphical way? Well, we can trace a line that represents the same amount of profit as a function of different numbers of chairs and tables. So if we take the cost function, the objective function, and we plot it for some values, we can get these lines here, okay? So these are going to be representations of our profit for different combinations of chairs and tables. So the idea here is that the more we go in this direction, the more profit we make, okay? And this profit, for instance, this amount of profit corresponding to this green line over here, can be obtained with different combinations of tables and chairs, okay? For instance, we may build 2.5 chairs and 2 tables. Now, 2.5 chairs doesn't make sense, of course, to you, but we can consider, for instance, these numbers should be multiplied by 10,000 units. And so 2.5 actually doesn't, it means essentially 25,000 chairs, okay? So it doesn't matter that we have decimals here. We can make sense of the problem anyway. So the idea is that we want to, of course, build as many chairs and as many tables as possible along these lines over here. And as we push these lines as high as possible, we will end up with the last point in the feasible set. So this is going to be our last point in the feasible set, and it's going to be the optimal solution of this problem. Let's look now at another example, which comes from machine learning. Of course, machine learning now, and more generally AI, it's a very popular topic, it's a very hot topic, and all AI, it's based on optimization algorithms, okay? So generally what you want to do is you have a certain model, and you want to match certain weights to train that model. Okay, so you want to determine those weights to find the best model that can produce the outputs that you want. And the simplest example of this type of problems is a classification problem. In the classification problem, the idea is that we have, in this specific instance, two sets of points, okay? Some red points and some blue points, which are plotted over here. And what we want to do is essentially to find a classifier. So a classifier is a rule that tells us if I give you a new point, we can use this classifier to know if this point is blue or red. So the idea is that we use a bunch of red and blue points to train our classifier, and then we use our classifier on new points which we do not know if they are red or blue, and then we use this classifier to determine if they are red or blue, okay? Now here we see two examples of a classifier. The first classifier is it's this line over here. It's a linear classifier, and as you see, it's not very good. It's actually has a poor accuracy, and the reason is that this set of points cannot really be separated or cannot be separated with a good approximation using a linear classifier. This is a classical example of a set of points that can be separated only using a polynomial or nonlinear classifier. And here we see over here a different classifier. So the objective here is to design an optimization algorithm that finds the best classifier for this set of points. Okay, so that finds essentially this curve over here. And again, this is a problem that it's a very simple problem, which has a graphical representation for which we can find a solution by just looking at it. But this is just for simplicity. Of course, you want to do this for very complex problems for which you cannot find an easy solution by just looking at it. These are essentially the three problems, essentially that three examples that we have seen. And now let's delve more into the maths. And I will keep it very simple for this first lecture, okay? So I just want to introduce some language that I will use starting from the next video. And the language is the following, okay? So what is an optimization problem? Well, an optimization problem is something which has this form over here. Okay, usually it has a certain predicate, a certain verb that tells us if we want to minimize or maximize a certain function. And this function over here is called the objective function. Now, depending on whether we want to minimize or maximize this objective function, this function can also be called the cost function, if we want to minimize the cost, or it can be called the reward function if we want to maximize our reward. And then, so the problem is to, for instance, here minimize the cost function, but this is subject to certain constraints, okay? So we have these additional lines which are called constraints. And the constraints are codified by two types of mathematical relations. The first ones are sets of inequalities. So we have some functions of x indexed by I. So we have f1 of x, f2 of x. So a certain number of functions which needs to be less or equal than 0. Okay, so this is our codification of our inequality constraint. And the other set of constraints that we have is the equality constraint. So we have that a certain function has to be equal to 0. Now, the fact that we're talking about less or equal than 0 rather than less or equal than a number or a function is without loss of generality, okay? It's just a matter of changing the name of f, so we can redefine f, so to write it always in this form. For instance, if we have that f1 of x has to be less or equal than g of x, then this can be written as f tilde of x equal to f1 of x minus g of x less or equal than 0. So you can see that this can always be written in this form over here. And it's the same for the equality constraint. And the understanding of what is this meaning, it's quite clear over here, okay? So equality and inequality constraints tells you, for instance, a limit in the amount of resources that you have for your optimization problem. And that's just an example, okay? The general idea is that any optimization problem can be formulated in this general framework, okay? So we have this set of constraints which are called inequality constraints, and then we have this set of constraints which are called equality constraints. If there are no constraints, so if there is no constraints in our problem, then the problem is called unconstrained. Now, one thing to distinguish is the concept of local optimal and global optimal point, okay? So the idea is that if we have an optimization problem in which our cost function is the following, well, we know here that the solution, the minimum cost, is going to be this point over here, right? And this is the global solution. It's always true that that's the minimum. But if instead we have something like this, then we see that we have this solution here, which is actually the global optimal solution, but there is also this point here, which is not a global solution, but it's still good with respect to a certain region, okay? So it's still good around this region over here. And that's called the local optimal solution. Now, why do we care about local optimal solutions? Well, because in practice, in the majority of practical problems, it's very difficult to find the global solution to our problem. And so the best thing that we can do is to find a local solution and maybe some bound on how suboptimal our solution is. Sometimes we cannot even find a local optimal solution, we just get an approximation of our solution. But yeah, generally speaking, the majority of optimization will find local optimal solutions. The exception is convex optimization, and that's why we're going to cover convex optimization. Now, before concluding, I want to show this idea that I will share with you also code to actually solve problems in practice. And here we have an example of the code. So this is a very simple example. I'm not going to explain this today, and I will explain this maybe in about 4 or 5 lectures after we have covered a little bit of simple theory. And after that's covered, then we will look at how we solve these problems. And for instance, we are trying to understand this piece of code here. Okay, but if you already want to have a look, you can read the code yourself, and then there is a nice plot that represents the solution to this problem. In particular, for this problem, the objective function has essentially this shape here. So it's a 3D shape. Okay. And then in addition to that, there is a constraint which is essentially a line. So it means that we need to be on the line, and on the line we need to find the smallest point on this 3D parabola, okay? And it turns out that, so it means that essentially the unconstrained optimal solution is going to be this point over here, but this is not in the feasible set. So the feasible set is only the points which are on this line over here. And then we know that in this direction over here, we go lower, and in this direction over here, we go higher. And so we look for the best solution, and the same over here, okay? So we go high in this direction, and we go high in this direction. And it turns out that the best solution is going to be this point over here, which is, if you look at it, you can think of it as the closest point to the unconstrained optimal value, okay? Again, this is just an example. So this concludes this introduction to the Optimization Masterclass. I hope you enjoyed this introduction and that you will start to follow the rest of the series. So see you next time.